space. So I'm going to be talking about various recent papers that have appeared in the last year. The first with Nima Lashkari and Michael McDermott, then a paper around New Year's with Tom Faulkner, Monica Aguica, Tom Hartman, and Rob Myers, and then finally a recent paper with Brian Swingle. So the background is that there's now a good body of evidence for an intriguing connection between the entanglement structure and the dual space-time structure or geometry in examples of the ADS-CFT correspondence in holographic conformal field theories. And so given that connection between entanglement structure and space-time structure, it's a natural question to understand if we can actually make a connection between dynamics of space-time and some properties or dynamics of entanglement. So that's the goal of this talk. And what we'll show is that a very basic property of entanglement in conformal field theories that I will explain. So given this property that's true of all conformal field theories, if one applies that to a holographic conformal field theory, and actually the notion of holography that we need is very weak, so I'll say exactly what we assume, then the geometries dual to states near the vacuum state of the conformal field theory must satisfy Einstein's equations linearized about anti-de Sitter space. Okay. And that actually, recently we've understood that includes a source term which involves all of the bulk matter fields. So the starting point is to recall the definition of entanglement entropy. So if we have any quantum system that I could divide into two subsystems, A and A bar, then to define entanglement entropy, you calculate the density matrix for the subsystem A, and then you calculate the von Neumann entropy for that density matrix. And this provides a quantitative measure of entanglement between this subsystem and this subsystem. Okay. So now I want to demonstrate a result about what happens to the entanglement entropy if you vary the quantum state. So we imagine starting with some state of the entire system, and then we change it a little bit, and immediately from the definition of entanglement entropy, what we find is that the variation of the entanglement entropy for the subsystem is equal to this expression that involves the variation of the density matrix, and then the log of the original density matrix. Okay. And so that seems fairly trivial, but in fact it's quite useful in many cases if we have knowledge, if this original density matrix takes a nice form. So let me give you a few examples. Okay. So the first example is where the subsystem A is just any quantum system with some Hamiltonian H. And this system is weakly coupled to a heat bath, as we usually have in the canonical ensemble in thermodynamics. So in this case, if we assume that the system A is at a particular temperature, then the density matrix takes the usual form for the canonical ensemble. And if I insert this density matrix into this expression here, then what I end up with is the first law of thermodynamics. Okay, so it's not so trivial, even though it was a one-line variation from the definition of entanglement entropy. In particular, it's actually a very interesting quantum form of the first law of thermodynamics. So it's an exact statement that says that if you start from the density matrix here, and then you make any variation, not just a variation to some nearby equilibrium state, then the change in entanglement entropy, okay, which is the same as the thermal entropy if you're in an equilibrium state, but more generally it's the change in entanglement entropy is equal to 1 over T times the change in the expectation value of the Hamiltonian. Okay. So next I'll talk about a quantum field theory example. So if you have any quantum field theory on Minkowski space, then a famous result is that in the Minkowski space vacuum, the density matrix for the half space is a thermal density matrix where the Hamiltonian is taken to be the Rindler Hamiltonian, which is just the generator of boosts in this wedge of space-time. Okay, so this is the famous result of Unruh, equivalent to saying that accelerated observers will see a thermal spectrum of particles. Okay, so in this case, again, we have an explicit expression for the density matrix. We can plug it into the formula on the earlier slide, and now we get a result that says, if I start from the vacuum state in Minkowski space, and I vary this state, then the variation of the entanglement entropy for this half is equal to this particular, now I've plugged in an explicit expression for the Rindler Hamiltonian, and there should be a delta there. It's the variation of this integral involving the expectation value. Okay. Now a third example, which is the one that we'll use in this talk, follows easily from the previous example. Okay. So now instead of a general quantum field theory, I'm focusing on a conformal field theory. And in a conformal field theory, so we have additional symmetries. In particular, we can make a conformal transformation that maps this Rindler wedge that we talked about in the previous slide to the domain of dependence of this ball-shaped region. This is a ball-shaped spatial region, the interior of a sphere, and its causal diamond or domain of dependence. So there's a conformal transformation that maps this region to this region. Okay. And since we know if we're in the CFT vacuum state, then we know the density matrix for this region. And so we could use that conformal transformation to deduce what is the density matrix for a ball-shaped region in a conformal field theory. Okay. And it's just the same kind of expression, except instead of the generator of these Rindler time translations, we get the generator of whatever those map to in this region here. Okay, so that I'm calling H zeta. Okay. So for a conformal field theory, if I have a ball-shaped region as my region A, then again I know the density matrix explicitly. I can plug it in to my expression. And I'm going to use this explicit expression for that generator. Okay, so it's an integral involving the stress tensor. And so the result, and this is the key result in conformal field theory that we'll be using, is that if I start with the vacuum state of a conformal field theory, I consider any ball-shaped region, and now I vary the state of the full conformal field theory, then the variation of the entanglement entropy for that ball-shaped region is equal to the variation of this integral involving the expectation value of the stress tensor. Okay. Importantly, both sides of this expression are finite for well-behaved variations. So the entanglement entropy in quantum field theory is a quantity that typically has divergences, but when we're talking about these variations, these things are finite as long as we don't do anything too crazy. Okay. So this result was derived and emphasized in a paper by Blanco, Cassini, Hung, and Myers. Okay. So now we're going to move to the holographic context. Okay. But in fact, I don't need to assume very much at all. So I'm not going to assume all of ADS CFT or string theory. Let me just state exactly what we need to assume for the result that I want to derive. Okay. And this assumption is motivated by the observation that for some conformal field theories, okay, the entanglement entropy for the vacuum state, calculated for all the different ball-shaped regions of various sizes, happens to match the area of extremal surfaces in an auxiliary ADS space. Okay, so if I have a region here, I draw the analogous region on the boundary of ADS. I find the surface of extremal area whose boundary matches the boundary of B, and then the area of this thing properly regulated matches the regulated area, entanglement entropy here. Okay, so this is the observation of Ryu and Takiyanagi. Okay, so here's the basic assumption that I'm going to make, motivated by that. So suppose that we're looking at a conformal field theory where that connection, where we can compute the entanglement entropies geometrically, at least for a family of states near the vacuum state. So to say that again, suppose that there's a family of perturbations to the vacuum state, not necessarily all perturbations, where for each of these ones, there's some associated perturbation of anti-de Sitter space, such that if I want to know the entanglement entropy in this state for this region, all I have to do is compute the area in this geometry for this associated extremal surface. Okay, so that's our assumption. In explicit formulas, I'll often describe these perturbed spacetimes using Pfefferman-Graham coordinates. So we have pure ADS, and then I'll describe the perturbation by a function capital H. Okay. So our question is, given this result in conformal field theory, and given our assumption that relates this side to some geometrical quantity, what does this equation, what does this CFT constraint, tell us about the perturbation of the metric? Okay. So the first thing I'm going to do is consider that result in the limit where the ball becomes very small. So in the limit, so here's the result. I'm going to take a limit where the ball becomes very small. And it turns out that this side, once I map it onto the gravity picture using our assumption, it actually just gives me a particular component of my metric perturbation in the limit as you go to the boundary. It actually gives you H0, 0. The left side, if I take the limit of a very small ball, turns out to give me, remember it was an integral over the stress tensor over the region, but now the region is getting very small. So the left side turns out to give me just the expectation value of the stress tensor at that point. Okay. And there's some powers of R that match on both sides. So if I apply this equality in the limit of the small ball, what I end up deriving is that the expectation value of the stress tensor in the CFT must be equal to the asymptotic metric. So we've derived, based on that simple assumption, and our, what I'll call the first law for entanglement, we've re-derived this holographic stress tensor prescription. Okay, so we don't need to assume that going forward. We can derive it. Okay. Now we'll go to the case of a general ball. Okay, so we have that delta S is equal to this integral. Our assumption allows us to replace delta S with the change in area of this extremal surface as we vary the metric. Okay. That change in area can be written to first order as an integral over the original surface of the metric perturbation. On the right-hand side, we can use the result from the previous slide to re-express the expectation value of the stress tensor in terms of the asymptotic metric. Okay, here I've used that it's a conformal field theory to say that T00 is equal to Tii, and then I use our holographic stress tensor to replace that field theory quantity with a gravity quantity. Okay. And so what we end up with is a gravitational version of this delta S equals delta E. And the gravitational version says that this integral over the bulk surface inside is equal to this integral involving the metric perturbation over a bulk surface at the boundary. Okay. So here's just a visual representation of that. Okay. Here's my perturbed ADS space. I can choose any ball on the boundary, and the CFT constraint is telling us that whatever the bulk metric is, some integral over this surface has to equal some integral over this surface. Okay? So this is something that will be true for some choices of H and not true for other choices of H. Now, interestingly, if we make an identification between our choice of ball here and the point at the tip of that surface where the surface reaches furthest into the bulk, what we see is that there's a one-to-one correspondence between the choice of ball and points in the space-time. Okay. And since we have one constraint for every ball, another way to say that is we have one kind of non-local constraint for every point in space-time. And that motivates the question, can we actually turn that set of non-local constraints into one local equation? And the answer turns out to be yes. So this is morally equivalent to going from the integral versions of Maxwell's equations to the differential versions of Maxwell's equations. So here's how it works. It turns out that there exists a differential form in the space-time that one can construct in terms of that metric perturbation and your particular choice of ball, such that the integral of this differential form over B is the variation of, is delta E, that boundary integral. And the integral of this form over the interior surface is our delta S. And furthermore, the exterior derivative of this form gives us something in which the time-time component of the Einstein's equations, or the left side of the Einstein equations, in terms of H appears. Okay, so the exterior derivative is the volume form on sigma times some positive function times this component of Einstein equations. Okay, so now we're going to use Stokes' theorem. So we start out with our non-local constraint that says this integral equals this integral. Okay, from what I just said, this integral is equal to the integral of that form, and this integral is the integral of the same form. Okay. So we can combine that, noticing that B minus B tilde is the boundary of this surface sigma, the spatial region sigma in the bulk. We can say that our gravity constraint is the same as saying that this form integrated over the boundary of sigma is 0. And then we apply Stokes' theorem to say that the derivative of our form integrated over sigma has to be equal to 0. Okay. So the bottom line is that we've translated our non-local constraint into this thing that says that the integral over sigma of this thing involving the TT component of the Einstein equation has to vanish. And it has to vanish for all possible choices of sigma, these hemispherical regions inside ADS. Okay. Now this arrow is not quite as trivial as it might seem, but from that it turns out one can prove that the only way this is possible is if this TT component of the Einstein's equations for the metric perturbation vanishes everywhere in ADS. Okay. So what about the other components? So far, we have used a particular definition of time on the boundary. We were talking about spatial balls, and implicitly I was talking about some particular choice of spatial slicing on the boundary. Okay. But these conformal field theories are Lorentz invariant, and everything that I can do in one frame of reference, I can do in any other frame of reference. So if I express the result that we just had, I can express that in a more covariant way to say that we chose some definition of time associated with a velocity vector u. Okay. And with that definition of time, what we showed was that u nu times delta E mu nu is equal to 0. Okay. Well, I could do that for any definition of u. I could use an arbitrary u. Everything goes through in the same way. And so it must be true that this is 0 for any u. And from that, it follows that the Einstein equations, the linearized Einstein equations for any components mu and nu must vanish. Those are actually not all of the components because mu and nu were field theory directions. There's also the radial direction. But it turns out that the tracelessness of the stress tensor and the conservation of the stress tensor in the CFT, those imply that these boundary quantities vanish, which turn out to imply that these components of Einstein's equations vanish at the boundary. And those components of Einstein's equations turn out to be constraint equations. So using the other components of Einstein's equations, we can propagate these in and show that actually the remaining components of Einstein's equations are also satisfied. Okay. So the summary so far is that we proved this relation that holds for all CFTs. We made a basic assumption that for certain CFTs, some states near the vacuum state also have their entanglement entropies computed geometrically by some corresponding geometries. And then what we showed was that, according to that assumption, these geometries must satisfy a particular non-local constraint or a family of non-local constraints. And then it was a relatively simple mathematical derivation to show that those non-local constraints are exactly equivalent to the local Einstein's equations. Okay, so we've derived that in any kind of holographic theory, space-times dual to CFT states near the vacuum must satisfy Einstein's equations. So far, all of that was at the leading order in large N. Okay, so when we made our assumption that the entanglement entropy was equal to area in the bulk, that's actually understood to be a large N statement. It doesn't include bulk quantum corrections. So fortunately, there has been a recent proposal by Faulkner, Lukowitz, and Maldacena for how to interpret CFT entanglement entropies beyond leading order in large N. So what are the 1 over n corrections? Or equivalently, what are the g Newton corrections on the gravity side? And their formula says that you have the area term, and then this is corrected by a bulk entanglement entropy term. Okay. So in terms of this diagram, the CFT entanglement entropy for this region is equal to the area of that surface over 4g Newton plus the entanglement entropy of the bulk fields inside that region, sigma. Okay. So that's a quantum correction. So what we want to do is just repeat the whole derivation, but include this term. So now what does that term give you? Well, so the magic is that we can re-express this term in terms of the bulk stress tensor. And the way to do that is to realize that that region sigma, it's actually a Rindler wedge of ADS. Okay. And this argument that I gave before that said, well, we actually know, for any quantum field theory, we know the density matrix of a Rindler wedge. That was for Minkowski space, but it works in ADS as well. And so I can actually compute this bulk entanglement term in terms of the bulk stress tensor. I plug that all in, again, to the same derivation. And what I end up with is that with the 1 over n corrections, you now have that the linearized Einstein equations for H are sourced by the expectation value of the bulk stress tensor, which includes all bulk quantum fields, including the metric perturbation. Okay. So in some sense, what we've seen is that this is a derivation of the universality of gravity. The reason why all of the fields source the metric is that all of those fields contributed to the entanglement entropy in the bulk. And I have 0 minutes left, so I'll stop there.
Rosie?
Thank you very much. So I have a question. So I think what we are trying to do, if I understand it correctly, is to try to state the bulk dynamics, in particular equation motion, in the language of conformal field theory on the boundary.
Yes.
And if I understand what you did from the point of view of Ward's formulation of entropy, then main thing is the diffeomorphism invariance in the bulk. And so it seems to me that you can translate Einstein equation in this way, and I can imagine that you can do something like that also for Maxwell equation because of the case symmetry. But if we want to understand the entire bulk dynamics, you also have to understand, for example, scalar field, possibly with potential.
Yes.
Can you see that there is a way to translate those kind of dynamics also from boundary CFT language?
Yeah, so one of the things here is that, so we have many possible examples of holographic theories. And if you ask what is universal on the gravity side, well, some of those theories will have scalars, and some will have gauge fields, and et cetera. But really, the universal thing is that you have a metric. Okay? And so somehow what's happening here is that we're translating a property of a universal field theory thing. So this entanglement entropy is something that can be computed in any field theory. Doesn't matter what kinds of fields you have. It's just an inclusive universal quantity. And we're translating that statement to a universal statement about holographic, about the gravity theories. So I'm a little bit, so it seems maybe unlikely that something completely analogous to this could give you the rest of the equations. Although, yeah, someone pointed out, Emil Martinek pointed out in the break that, well, maybe you get a little bit more in supersymmetric cases. Maybe there's some kind of supersymmetric version of this that would give you equations for at least some of the other fields.
Could you comment on the key obstacles to uplifting all this to the nonlinear?
Okay, good. So let me make a few comments about the nonlinear case. Okay, the first one is that once you have the linearized equations and we have a stress tensor operator on this side, so one thing you can say is that assuming that there's some local equations that operate at the nonlinear level, if we ask, well, what is the source term in those equations? Well, the source term has to be something which is equal to the stress tensor plus possibly something else. But what if there's any other operator there as the source, then the delta of the expectation value of that other operator would have to vanish for any, it can't give any contributions to this linearized result. Okay, and the only operator, well, in fact, if you demand a local operator, then there's no other local operator where delta S is equal to delta T. And so, in some sense, this linearized result, if you also assume locality, it tells you that it's the stress tensor that should be the source, even at the nonlinear level. And then various people in the past, perhaps not in the ADS context, various people in the past have argued that if you have linearized gravity and that the stress tensor is the source, that the only consistent way to have a consistent theory out of all that is to end up with some full nonlinear theory like Einstein's equations. A separate comment is that, so that involved an additional assumption, which was locality. A separate comment, is that this relation here, which is a statement about small perturbations to the vacuum state of the CFT, this actually generalizes to an inequality for finite perturbations. So it says that the change in the entanglement entropy for a ball-shaped region is always less than or equal to the change in this definition of energy for that ball-shaped region. Okay. So that inequality, if we apply our basic assumption, that gives us a constraint on any nonlinear geometries that are dual to CFT states. And I'm currently thinking about exactly what does that constraint tell you. Can you express that in some nice way in the bulk? It's an inequality, so it's not going to give you something like nonlinear Einstein's equations, but it should tell you something that has to be satisfied about geometries in any quantum theory of gravity.
Anyway, I think it's time to thank the speaker again. Sorry for more questions.